Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 30. On the right is a figure showing a conducting metal bar sliding to the right with a constant speed v equals 5.65 meters per second along a pair of parallel metallic rails which are connected to a resistor of resistance R equals 12.2 ohms on the left hand. Penetrating the plane of this system is a uniform magnetic field B which is directed into the paper. Its magnitude is B equals 0.545 teslas. The distance between the two rails is D equals 25.3 centimeters. A. Find the magnitude and direction of the induced current in the circuit. Choose the direction of the motion of the metallic bar as y-axis. And let us color the total area traveled as A, and it is calculated as y times d. Therefore, the magnetic flux V times A changes in time. Remember that the induced electromotive force is the negative of the first time derivative of the flux. The negative sign indicates the Lenz's law, but we do not use this sign in the calculation of the induced electromotive force. Therefore, we write induced electromotive force equals d phi b over dt. Phi b is b times A is y times d, but b and d are constant and can be taken outside the differentiation. Then we get b times dy over dt. In the problem, dy over dt is the constant speed v. Then we have b times d times v. At this time, we can put the numerical values into this formula. Then the induced electromotive force is obtained as 0.77905 volts. If you remember from the class, the increase in the magnetic flux B dot A is reduced by the induced magnetic field which is out of the screen. By the right-hand rule, current induced in the circuit which is counterclockwise. This induced current leads us to assume that as if there were induced electromotive force with the negative and positive polarities like this. Therefore, the induced current is calculated by the Ohm's law. We know the numerical values. The induced current is 0.059019 amperes, which is approximately 59 milliamperes. B. What is the force required to move the metal bar with constant speed? The magnetic force on the metal bar due to the magnetic field is calculated by the formula I times L cross B, where L is the current length vector. The direction of FB is found by the right-hand rule as to the left. Therefore, to move the metal bar with constant speed, the applied force on the metal bar has to be to the right, which is equal to Fb in magnitude. L cross B can be written as L times B times sine theta, where L is d. The angle between vectors L and B is 90 degrees, therefore sine 90 degrees is 1. So applied force has magnitude I times d times B. With the numerical values, it is obtained as 8.1378 times 10 to negative 3 newtons. Or in 3 digits, it is approximately 8.14 newtons. C. Calculate the power supplied by the force into the system. Power has the formula F times V. We know the numerical values. Therefore, the power supplied by the force into the system is approximately 0.0460 watts. D. Calculate the power dissipated in the resistor. The power dissipated in the resistor has the formula I squared R. We put the numerical values into this formula. Therefore, we obtain the power dissipated in the resistor as approximately 0.0460 watts. The power dissipated in the resistor is equal to the power supplied by the force into the system, as it must be. Okay, this result brings us to the end of the discussion of this problem. Thank you for your attention. See you on the next video.